Special thanks to Dgtronix and for inviting me to attend this conference, and also thank you to Dgtronix for sponsoring my paper and for providing demo equipment, and mostly thanks to you guys for showing up, because otherwise I would be talking to an empty room, and that's not nearly as much fun. I do like to talk, so at the end you might have to give me a quick kick to stop. Starting is pretty easy, stopping not so much. But today I want to talk about creating VRM models, and creating VRM models is kind of a little bit controversial. And I said it at my keynote in China, that if you took 10 power integrity engineers and asked them a question, you'd get at least 18 different opinions. And when it comes to VRM modeling, it's not any different, really. You might have noticed that there's a sparring match going on between myself, Eric Bogdan, and Larry Smith about what it really takes to create VRM models and whether or not they're even needed. Most power integrity simulators aren't capable of simulating a VRM model, and so Larry Smith and most other power integrity engineers use RL equivalent models. And that's kind of absurd if you think about it. The power source is one of the largest noise sources in the system, generates noise in at least 5 different ways, and I'm not sure exactly how we replicate that with a resistor. And so it doesn't really work. For those that are interested, I actually have an article, I guess I'll call it, in the July issue of Signal Integrity Journal, and it's titled The Essential Need for Characterizing VRMs and Why It Is That We Really Need a Full VRM Model. But the reasons we created, there's really 4 reasons. One is that we want to optimize our designs, and a lot of what we do in power integrity is about trying to achieve flat impedance. And how do we do that? How do we optimize the design? And one of the keys to achieving that is models. Another reason we make high-fidelity models is because we need to troubleshoot things. And I know most of you have never had anything that didn't work, but there are engineers in the world that created things that don't actually work the first time. And if that's the case, then we might need a simulation model in order to troubleshoot it. A lot of what I do is power integrity analysis, and so in order to perform power integrity analysis, we do need the VRM. And it's an important element of the power integrity distribution network. So we need a model for that. And of course, for those of you that are in high reliability, we also needed it for tolerance analysis. How do we figure out what it is that worst case performance looks like? And we use the model in order to generate what worst case performance looks like. I wanted to use this very simple example just to kind of show some pictures up front about where it is that I really want to get to and what it is that I mean when I talk about optimizing a design. And so this image on the left, this is actually a VRM, a small switching regulator made by Texas Instrument. And we measured the impedance, and like you'd expect any good power integrity engineer to create, you would not expect it to be a nice flat line. And I would say that, well, maybe Texas Instrument doesn't understand power integrity yet, but that's certainly not a flat impedance line. Our goal in power integrity is to achieve flat impedance. We took Texas Instrument's part, we optimized the design, and we sent it back to them, and now it's a nice flat line. And how do we do that? We do that by creating an accurate VRM model. In both cases, you can see we made the measurements in the simulations in order to verify that the performance was exactly the way we expected and to assure the validity of our model. Here's another one. This one is for troubleshooting, and this one I had to actually laugh at. I wrote this paper with Xilinx and Keysight, and it was interesting to me because Xilinx knows their FPGA better than anybody on the planet. They make it. They know what's on the package, they know what's on the die, they know everything about it. And they created a demo board for their 32 gigabit transceivers. And in order to make the power splice, they tapped Texas Instrument, who I just said doesn't know much about power integrity, but they are the largest power supply company in the world. And of course, their power supply did not work. The board did not work. And I have to laugh at that because I say that if Xilinx, along with the largest power electronics company in the world, are not capable of creating a demo board to run their own part, then how are the rest of us supposed to accomplish this? I think we're doomed. Why did they call me? They called me because they had an impedance profile that they couldn't really live with. Their transceiver couldn't work with that. They chose a power supply that had no compensation networks of any kind. In fact, no pins at all. So there was no way to modify the design, and yet they needed to make the board work. And they said, Steve, can you do it? And the answer is, of course, but we need an accurate model because the model tells us what it is that our degrees of freedom are. We were able to fix it. I wrote a paper about it for DgCon 2018, and I did an update of that paper with Xilinx and Keysight at DgCon 2019 earlier this year, just to show that Xilinx actually did learn their lesson, and they learned how to design a power supply, and unfortunately, I don't know that Texas Instrument learned anything at all. Tolerance assessment, we do need to look at tolerances. It's one of the big reasons we do this, and I'm going to talk a little bit about voltage mode control and current mode control, and the differences between them. And the model tells us a lot of things about the difference between them. And honestly, a very large part of what I do in a consulting arena is trying to fix things that didn't really need to be fixed. It was just poor choices from the start. So much about power integrity is about selecting the right parts from the beginning. And if you don't do that, digging yourself out of the hole that you find yourself in can be quite troubling. And so what we want to try to do is we want to try to understand the degrees of freedom, and we want to try to deal with those right up front where they're not so hard to fix. So we need a unified model to do this, and I wrote my first VRM model in 1990. I published it for the very first time in 1996. Why did I write my own model? There were plenty of good state-space models that were available from the universities, and Dr. Chuk had one, and Teslaco had one. Why did I write my own? I wrote my own for a very specific reason. And the specific reason was that I needed something that could cross the boundary of continuous control and discontinuous conduction mode. I needed something that could operate across the boundary. Sometimes at low current we're discontinuous and higher current we're continuous. And of course I can't say, wait a second, stop, I got to switch models here in the middle of my pulse. I needed a model that could actually run both modes. And so that was one reason I wrote my own model. Two other reasons. One is that I needed a unified model that could operate in both current mode and voltage mode. And most models weren't able to do that. And maybe even more importantly, I needed something that could do not only small signal analysis, which most state-space models are designed for, I also needed something that could do large signal. The differences are really profound. So in small signal, we're looking at small perturbations, and we look at the responses of the perturbations. But in the real world, not everything is small signal. In fact, the first use of my model was to perform a simulation of the International Space Station as it goes through eclipse. And when it does that, some really interesting things happen. It's, when it's in sunlight, it's powered by the sun, and the photovoltaic arrays are running, and they're running battery dischargers and charging batteries and stuff. And then all of a sudden, it goes into the dark. And when it goes into the dark, it's running battery dischargers. And those are very large signal transients. We switched from one bus to another bus in real time. Of course, we have astronauts on the International Space Station, so one of the things we really wanted to try to do was to get it right, because that way we keep the astronauts alive. But we needed something that could cross those boundaries. 2010, I made the first update to my model, and it was because National Semiconductor had decided to do something called WebBench. And they wanted to provide modeling tools to engineers that were internet-based. And you could go pick a part that they made, you could go on the internet and simulate it in real time. The problem was in 2010, simulators weren't nearly as fast, the internet wasn't nearly as fast, and here they were trying to run transient simulation over the internet. Didn't work very well, and they asked me if I could solve the problem, and I did. And the way that I solved the problem is that I used the state-space model, and I used the state-space model to drive switches so that we didn't need to solve voltage and current equations at every time step. We only needed to know when to start a pulse and when to stop a pulse, and it was much, much faster. I published that in 2010. In 2017, I made the next major advance in my VRM model, and that was to move the entire simulation model to a harmonic balance engine. Harmonic balance is a native Fourier simulator. There are no voltage equations or current equations. That makes it much, much faster. In a power world, it also gives us a couple of major advantages. One is that the actual answer is a spectral response, and that means that it's really well adapted to EM simulation. It's capable of doing things like EMI simulation, and of course we can reconstruct IFFTs, and using IFFTs we can recreate time domain measurements. Much like the model I did in 2010, it's based on the state space model that knows what the operation is, and so we're going to talk a lot more about that. I wanted to show you what a typical display looks like. So when we simulate a VRM model, we're simulating a lot of different characteristics. For example, we might want to see what the switch node voltage looks like. We might want to see what the spectral response of that looks like. Of course, we're interested in the flat output impedance, which is our PDN tool. We need to know what the large signal gain of the feedback amplifier is. We need power supply rejection ratios. The input impedance, of course, of a switching regulator is negative, so we need to know what the negative impedance is. We need to know what the passive components look like. We need the control loop response. We have current spectrum for the inductors and ripple currents, and we even have output ripple voltage. Why did we go to harmonic balance? The reason we went to harmonic balance is I can do this entire simulation in about 500 milliseconds on my laptop computer. Blazingly fast. And all of this is created from a very simple model that I'm going to show you how to create. But first, nothing's free. Everybody knows everything comes at a price. And so to get this blazingly fast performance, we do have to make some trade-offs. What are those trade-offs? Well, first, we need to understand that there's sampling poles in all of these switching regulators, right? Nyquist told us we need to have 2 data points for every cycle, and because it's a sampled phenomena, we do see what appear like transmission line effects in both the voltage loops and the current loops. Those appear at half the switching frequency. But those only appear if we're in continuous conduction mode, not in discontinuous conduction mode. And of course, the model is running back and forth across the boundary. It can't figure out when to apply a transmission line and when it can't. So we left it out. The current mode sampling pole is different depending on how it is that the current is sensed. So there's what they call emulated current sense, where they sense the current in the top MOSFET, actually by looking at the current in the bottom MOSFET, and they call that emulated current mode control. They do that because the on time of the bottom switch is much longer than the on time of the top switch, and so we have much better settling time and a much lower noise environment to make the measurement. But the current pole looks different in emulated current mode than it does in peak current mode, and that looks different than average current mode. And so each one of these have finite differences. And we ignored all of those. We ignored all of those because they're at a high enough frequency that we don't really think that we need them, and I'll show you why. In order to do all of that, we restrict the bandwidth of our model to 1/6 the switching frequency. As we go above 1/6 of the switching frequency, those sampling effects start to become obvious, and the sampling poles in the current loop also start to become obvious. Below 1/6 of the switching frequency, they're not. And so we can build a very accurate model, but only up to 1/6 the switching frequency. In order to make sure that it's subharmonically stable, that also means that we do have to assume that they did adequately compensate the current loop using a slope compensator, and that's almost always true. And of course, we also need to make sure that the VRM has no chaotic behavior, right? We're assuming that this is a steady state machine that has every cycle is repetitive. It's not a hysteretic type controller which doesn't linearize at all, right? We're linearizing the performance, and that means that it must be linearizable. If we look at a typical VRM, it looks something like this. There's a feedback amplifier. There's a modulator that's made up of the driver, the switching MOSFETs, and the pulse width modulator comparator. And then there's an output filter that averages the switching to make it look like a DC voltage, albeit with ripple on it. And we can break that into the 3 sections: output filter, planter modulator, and the feedback amplifier. And that's a typical voltage mode feedback controller. In current mode, it looks just a little bit different. And the only real difference is we added this red trace that says, okay, we're going to take some signal that knows something about the switch current, and we're going to add that into our feedback signal. So now we're actually looking at two things. We're actually looking at a ramp and the sum of the ramp and a signal that's proportional to current. That's what makes it current mode control. Now, the interesting thing about a VRM is it's a lot like an oscilloscope. When you take an oscilloscope, we see nice traces and pretty pictures, but that's not what the oscilloscope saw. The oscilloscope saw a bunch of dots, and then it figured out how to connect all those dots, usually using some type of interpolation. A switching power supply is made up of only two dots. There are only 2 points in time that we know about in a switching regulator. Only 2 points. And then we have to connect the dots. So the 2 points are the beginning of a switching cycle. We know that that happens. It's generated by a clock. And when the switch cycle starts, we turn on the top MOSFET and we start charging this inductor. There's only one other point in time that we know about, and that's the time that we decide to terminate the cycle. And that's when we turn the top MOSFET off. Everything in between those 2 points is interpolation. It's linear interpolation, and we can interpolate it based on the current flows, and that's how we do this mathematically. In the real world, there are actually about 10 different states, right? We can consider this VRM to be a state machine. There's 2 states. The top MOSFET is on, and the bottom MOSFET is on. That's it, 2 states. In reality, there are many minor states in between those two. The transition times between MOSFETs aren't infinitesimally small. They do actually have finite times. And so if you wanted to average those times, you could. There are propagation delays that delay the actions of when it is that we turn on a cycle, when we turn off a cycle. There are delays between the time we turn on the MOSFET, we turn off a MOSFET. There are losses that show up during switching, and all of those have small impacts on the switching cycle. I've written articles about many of them. If you really want to get into those details, you can. But for the most part, we really only need to worry about 3. The top MOSFET is on, and the bottom MOSFET is on. And of course, in discontinuous conduction, there's some point at which current just stops flowing. And in that case, for discontinuous current mode, we need to know where it is that that current stopped flowing. Again, we only started by knowing 2 points. We only know when we start a cycle and when we terminate a cycle. Now, of course, we have the feedback amplifier that connects to the modulator, and that's looking at a signal, and the signal is the sum of this current-based waveform and a ramp. And so we can say that the pulse width modulator resets when we turn off the MOSFET at the time that the control voltage is equal to the ramp plus the current signal times Ri. That's all very nice, but really all it says is that if we know what the feedback amplifier does, then we know when it is in time that the cycle terminates. And then we can linear interpolate. So we started a cycle right here. The inductor current ramps up until that point is satisfied, where the control voltage is equal to the sum of the ramp and the current signal, and we terminate the cycle, and once we terminate the cycle, the current starts to fall. Of course, we can calculate the slopes of those rises and falls because the inductor is connected either to the input voltage, the output voltage, or ground. And so we know what the voltage is across the inductor at any time, and that means we can integrate these. If the current does fall to 0, then it is in discontinuous conduction mode, and it's going to sit there at 0 until the next cycle starts. So we can actually reconstruct what it is that the current waveforms look like in this inductor during a cycle. And I can write the equations for those, and those are linear equations. So we have now linearized the entire operation of the switching regulator. There's only 2 modes of operation: continuous conduction mode and discontinuous conduction mode, and we know the difference by whether or not the inductor current got to 0. If the inductor current gets to 0, it's in discontinuous conduction mode. There are many VRMs that allow you to choose between forcing continuous conduction mode or disallowing discontinuous conduction mode, and there are those that allow it. And of course, we can go back and forth between the two. Many VRMs actually have a pin that allows us to select that, and we can change that on the fly. So how do we get from those equations to a model? That's not actually so hard. Every simulator has equation-based support. And so I wrote all of the equations that do all of that linearization for you. Anybody that's interested in the derivation, it's in my first book from 1996. It got republished last year. I have a couple of copies here. That doesn't work for you, write to me and I'll send you the derivation of the model. But that is the entire plant linearized based on those 2 points. And of course, there's many parameters that we need to plug in order for us to figure out what this VRM model does. One is that, like I said, we have this ramp. And that ramp, we don't really know much about it. It's inside the VRM model. And believe it or not, the semiconductor companies consider that to be secret sauce. So in most cases, they don't publish that number. They consider it a secret. I'm going to show you that it takes less than 5 minutes to unlock that code. And so I told them they're really going to need a better way to keep their secret because it's out. Not a very good lock they've got. Some controllers, this particular controller, we can see the ramp. I was able to take lots of different pictures of it. But there is a controller that I made for this ramp that's unified, and that means that we can use it in lots of different ways. It could be a fixed ramp. It could be a ramp that's dependent on input voltage. It could be dependent on output voltage. It could be dependent on the difference between input and output voltage. And so I call it a unified slope compensator. And it looks something like this. So we have a voltage ramp, and we can have a constant ramp, and we can also have it as a multiplication of a constant and input voltage, output voltage, or the difference between the two. And in current mode, you can see we have how these different constants apply and what it is that the value of Ri is. Now, how do I know it's right? I mean, my math isn't probably as good as a lot of engineers. I cheat a lot. I use MathCAD and stuff. I have a daughter that's a nuclear physicist, so if I get into trouble, I ask her to help me with my math. So how do I know I'm right? Well, the easiest way is to verify it against the gold standard. The gold standard, much as I hate to admit it, is Dr. Ray Ridley's thesis from 1990. And he published his thesis on small signal control and the cause of the subharmonic oscillation, which was the focus of his thesis. You can see it right there. And so what I did is I ran the Ridley configuration from his thesis using our model and his model so I can compare the two against each other. Here's the 1/6 switching frequency line, and you can see up to 1/6 of the switching frequency. Our models are very good agreement in both the power supply rejection ratio and also in plant gain. And we have a couple of other characteristics here also for different configurations. And again, you can see the 6th switching frequency line, and we end up with very good correlations up to 1/6 the switching frequency. And so that all works pretty good. Now we do have these parameters, and most of these parameters we know. We know what the input voltage is, we know what the output voltage is. If you don't know what the input and output voltages are, you can't be making a VRM model. Stay in that loop until you figure it out. You have to know the input and output voltage. We need to know about the output inductor, L out. And yes, we can measure it. We generally know what it is. Usually has a label right on it, and so we know what that one is. We'd like to know the DCR of it, of course. We'd like to know the RDS on of the MOSFETs, switching frequency, and the two that are really unknown, Ri and VRamp. And those two generally are considered to be secret sauce by the semiconductor companies. So I have those in red because those are the two that are supposedly under lock and key. If I look at the equations, I can actually write the equation for almost every parameter in a power supply. Again, my math skills aren't all that great, but I managed to get through it. And I can write the equation for power supply rejection ratio. I can write the equation for the output resistance. I can write the reverse transfer, excess inductance, control gain. What do they all have in common? Every one of them includes the two unknowns, VRamp and Ri, and I put those in red for you so you can see them. Every one of those equations has the two unknowns. Now you guys probably remember this from school, but if you want to solve two unknowns, how many equations do you need? Only need two. That says any two measurements, any two that I want, I can solve for the two unknowns. Take your pick, any measurement you like. In general, I like to pick output resistance, and that's because it's one of our focal points, right? We want this flat output impedance at the target limit, and that's one of our key focuses. So I like to use that one. That's a really good one. I also like to use power supply rejection ratio, and the reason for that is that power supply rejection ratio happens to have tremendous sensitivity to the voltage ramp. So I like to use those two, but you can use any two of these equations you want because every one of them includes both of those terms. Two equations, two unknowns, it's solved. Now in actuality, measuring RI is relatively simple for a current mode controller if the compensation pin or the output of the feedback amplifier is available. And the reason is because that voltage is going to change in proportion to RI. So if we just change the load current and watch that voltage, we can draw the straight line, and the slope of that straight line, that's RI. We can actually figure that one out with a voltmeter. Not so hard. I picked a bunch of different points, but you can see the line is very, very straight. So in general, we really only need 2 points. And of course, we can even figure out where the offset is. So you can extend that to 0, and you can find the intercept if you want to know what the offset is. And we can measure the output resistance. We're really only interested in the low frequency part. The low frequency part is resistive. Once we get above that, it starts to become inductive. But we can also get it from that measurement. Excess inductance is an interesting one. We like excess inductance because they say at DgCon that inductance is the root of all evil, and it's not true. What is true is that excess inductance is the root of all evil. Why do we have capacitors on our boards? Why do we need decoupling capacitors? We need those to absorb the excess inductance. So if I want to know what the capacitors on the board need to be, I need to know the excess inductance. I could write the equation for it. A lot of people aren't really comfortable with that. The equation's kind of yucky. There's another way we can do it. We can measure it. If we undersize the output capacitor, we'll see that nice resonance, and that resonance will also give us the excess inductance. From the excess inductance, we can compute stability. We can compute the value of the bulk capacitors needed. We can compute lots of different things once we know that. In fact, this is what I used to solve Xilinx's problem. I was able to see their excess inductance because the caps were too small. And of course, I did tell them that there was a simple solution because we absorbed that inductance by adding more capacitors. And if they just added another 25,000 microfarads per output pin, they would actually be just fine. Of course, they needed to find a place to put 25,000 microfarads per pin, and that was a little bit troubling. So you only get one other choice, and that is figure out how to drive the inductance down. How do you drive the inductance down? It's right here. Anybody that's interested, I actually did do a paper on it a few years ago in gigahertz bandwidth regulators. And why it is that everybody's so interested in gigahertz bandwidth, it's because the capacitors go to 0. PSR, we're also interested in the low frequency part of the curve. That tells us about the ramp and the slope compensator, and also it tends to be the easiest place to measure. So that works out really well, and it's a very simple measurement. We make that measurement on a frequency response analyzer, whereas the output impedance we make on a vector network analyzer. If you don't know the difference between the two, a frequency response analyzer is a 3-port instrument. One channel is an oscillator. The other two are high impedance receivers. And it does a simple calculation of the voltage at channel 2 divided by the voltage at channel 1. It does a simple division, which is very different than a 2-port vector network analyzer that has 250 ohm ports and it calculates S parameters. So to measure output impedance, we use S parameters. To measure PSR, we use a frequency response analyzer. There is something magic about the PSR. Ray Ridley wrote about this in his thesis, and he found that there was this, what he called audio susceptibility null. And that null said that at some voltage ramp level, you would get infinite rejection for PSR. And that's really good to know because it says that I can actually tune PSR and improve it just by the value of the slope compensation. But it's also a really good marker because I can go ahead and I can adjust my circuit and look for where that occurs. And then I have a good marker for where it is that I am, because this is directly related, again, to RI. So if you wanted to measure RI that way, you can do it directly from measuring where that audio null occurs. And so we could also measure the Bode plot. The Bode plot tells us about the control loop. We measure that in a frequency response analyzer, and we can measure the voltage and the phase, and we can calculate gain margins and phase margins and stability margins. We can do that if we want to. There's not really a need for us to, but the more measurements we can get, the better our model's going to be. Of course, we also need to measure the output capacitors. And most people get this backwards. They think that we design a power supply and then we choose capacitors for it. And it's not actually true. We actually select a capacitor and then we design a power supply around it. And the reason for that is that we have a lot more finite control in the control loop of our power supplies than we do in the selection of capacitors. For example, if for a given excess inductance, if I know I need a 100 microfarad cap or a 220 microfarad cap, I can go through the catalogs. Maybe you got your favorite vendor. I happen to like the red ones from Worth. They make really good caps. But when I go look for caps, they don't have so many 100 microfarad, 10 or 20 milliohm ESR caps. So I got to find one that's close to what I want. I won't get exactly the capacitance I want. I won't get exactly the ESR I want. And I probably won't even get exactly the ESL I want. I'm going to find the best capacitor that Worth can offer. Once I choose that capacitor, I have to tune all of the power supply parameters to match that. That's the trick. And so it's actually backwards. We actually select the capacitor first, and then we design a power supply around it. We measure that using a vector network analyzer. We export that into S parameters, and then we can make broadband models of it for those that are using SPICE. I gave you a link there. This tinyurl.com, there's actually 5 different videos under tinyurl.com/pi-videos. And one of those videos is how to make capacitor inductor models. But there's the measurement and the model overlaid. They're pretty close to perfect, and I can generally make that model in a few minutes. Same thing with the inductor. I mean, for the most part, you can probably read the inductor value off the inductor, but I generally don't trust measurements made by manufacturers. And so I measure them myself anyway. And there's the inductor model that we use. So now we have good models of the inductor capacitor. We're able to measure the ramp. In this particular case, it's available, so I could measure it. I was able to measure it at a bunch of different characteristics. Anybody here use MathCAD? Anybody? No? That's good. I got my first copy of MathCAD, I think it was around 1995. It's the only software package that I know of that has doubled in price and got worse every single year of its existence. And yet people still use it. Why? They use it for only one reason. It has this function called minimum error that is a least squares solver for unsolvable equations. But it does a least squares curve fit. That's the only reason anybody uses MathCAD that has gotten worse every year since it came out. Now we need to package all of that, and I've packaged all of this in many different ways, from LT Spice to P-Spice to iSpice, and the latest is ADS, Harmonic Balance Engine, but it also runs Spice. And so here's the plant. This is where all the equations sit. All of the equations are in this box, and there are just parameters to plug in. You plug in the parameters, it solves the equations. You never need to see the equations, and you never need to touch them. We pair that with our universal slope compensator, and again, that's parameterized. You just plug in the parameters. We don't need to know the equations. We just need to plug in the parameters. Now we need feedback amplifiers. There's 2 kinds of feedback amplifiers. There are voltage feedback amplifiers, and there are transconductance feedback amplifiers. Most modern pulse width modulators use transconductance amplifiers. Anybody know why? Huh? They're cheaper. And so it saves them money. And everybody knows that there's a difference between how you terminate them. Transconductance feedback amplifiers, you terminate compensators to ground. Voltage mode feedback amplifiers, you compensate with feedback in the feedback loop. Every book will tell you that. You probably learned that in school. Unfortunately, it's wrong. And proving it's wrong is very simple. I set two exactly similar gains, 3.215, 3.215. I took the transconductance feedback amplifier and I calculated the sensitivity to transconductance in both cases. And if you do what they tell you to do, you end up with about a 10 dB degradation in performance. I can't figure out why they want to steal 10 dB from you. I've asked them. Ingersoll had an interesting response. They said, Steve, you're really smart, and you're probably right, but we really can't get into that level of detail. And I said, so if you can't get into that level of detail, maybe you shouldn't have told your 10 million customers that they should do it like that. Maybe you should tell them you don't get into that level of detail. But almost every semiconductor company tells you to compensate it to ground, and very simple math proves that that's a really dumb thing to do unless you really want to give up a lot of performance. Now we could make a small signal feedback amplifier. It just takes voltage and it transforms it to a current, and so all we really need is a voltage to current converter that converts in microsiemens. Why don't we do that? We don't do that because that's small signal, and one of the first things I said is I needed to model it, small signal and large signal, and so we need a large signal model of that. So I also made parameterized voltage control and transconductance feedback amplifiers. This particular one is the transconductance model. It's a typical transconductance configuration, and it's fully parameterized. You can take the parameters right off the data sheet, plug them in, and you'll get large signal performance. The voltage feedback amplifier is quite similar, except that you can see there's a buffer on the output stage, and it's also parameterized. You get the parameters right from the data sheet, and you plug them in, and you'll get the right performance. But now I wanted time domain, and I wanted spectral content, and I wanted ripple and all that stuff. How do I do that? So that's where the magic is. The magic is that the state space model, the mathematical equations, calculate the 2 points that the VRM has. VRM only has 2 points. Start of a cycle, termination of a cycle. While that space model is running, it's blazingly fast. It's just an analog equation, and it's continuously solving the equation. That equation exports data in terms of a voltage source that says, here's my instantaneous duty cycle, which means the duration of my pulse, the time between the time I started a pulse, the time I terminated it. And that's continuously running out from the equations. All I need to do is take that information, reconstruct it back into a pulse, which I did right here. So I took a harmonic balance switch pair, an upper switch and a lower switch. There's a 1 volt voltage ramp here. And it says, okay, so I'm going to convert that duty cycle signal that goes between 0 and 1 for a 0 to 100% duty cycle, and I'm going to convert it back into a pulse train at the switching frequency, and I'm going to do that continuously while the software runs. And so the software is continuously putting out this pulse stream at the switching frequency. That's right here. And of course, it does the same output filter as the state space model, and now I get the reconstruction of time domain without having to solve voltage or current equations. Here's a simple example. LM25116, this is a VRM that's made by a national semiconductor. We made our own characterization board. We never use manufacturer's boards. We always make our own. So we took their circuit, we put it on our own board. We can get the RDS on of the MOSFET right from the data sheet for the MOSFET. Tells us right there, 22 milliohms. We can put in the parameters we know, input voltage, output voltage, switching frequency, the ramp capacitor, RDS on. The inductor, 3.3 microhenries. The capacitor is 820 microfarads, 7 milliohms. And we can even look at the timing resistor, and that tells us that actual switching frequency is 498 kilohertz. I can tell you when I assemble a characterization board like this, I measure every component. I know exactly what's on the board, so I don't need to worry about tolerances of components. I know exactly what it is that I normalized to. And here's all the parameters for the feedback amplifier that get plugged into our little feedback amplifier block. That's what it looks like schematically. There's the output capacitor measurement and model. There's the inductor measurement and model. There is the plant fully assembled, and you can see here's where the parameters go. There's the 3.1 microhenry inductor. There's the current sense resistance we calculated. There's switching frequency. There's the output inductor with its DC resistance. And here's the slope compensation stuff. All parameters, you just plug in the numbers. How well does it do? Here is our Bode plot. And you can see the comparison between the simulations and the measurements. They're nearly perfect. And if you want to solve that equation, you can. And if you don't want to, you don't really need to. You can see the, I wanted to point out that here's the transmission line effect that shows up due to the sampling criteria. And so our model doesn't necessarily show that, though we can include it if we want to. PSR can be a little bit tricky. One thing I do need to warn you about is at the low frequency end, very often the PSR is not actually from the controller, it's from your voltage reference. And that's one of the reasons that I like to get more measurements if I can. We were able to measure the DC voltage at different load currents, and I measured lots of points. I didn't need to, but I did. So I could show you this really nice straight line. The data sheet tells us RI is equal to ACS times RCS, and ACS they say is 10. 10 times 0.01 ohms. 0.1 ohms, very simple. Seems easy enough. We measured it. We get 0.115. That's really odd. We wondered why that was. We measured it on our board, and our board was even worse. Our board was 0.13. How can that be? Why? Really simple. This really nice tight loop is deceiving. This current signal is right here, and all the current is contained in what appears to be this little loop. Where did they put the current sense amplifier? Other side of the chip. So there's a DC ground loop that runs from the power plane that gets from this side of the resistor to the current sense amplifier where they measure it. It's not a differential amplifier. It's a single-ended amplifier. Anybody want to guess why they measured 0.115 and we measured 0.13? Took me a little while to figure this out. They used 2-ounce copper and we cheaped out a 1-ounce copper. And so our resistance was twice as high as theirs. And I like that lesson because that lesson says that we really do need to pay attention to the details. And yes, the printed circuit board got into the gain of the VRM. And so again, we like to make these measurement-based models. Here's the feedback amplifier. We took the data right off the data sheet. I printed it for you so you could see it. Here are the internal equations. You don't need to worry about those. This is all parameterized, but it plugs in all the numbers. You can see it got the right bandwidth and it got the right gain, and it also included all of the large signal information. So all the slew rates and things that would interfere with performance are all included. Tying it all together looks something like this. Here's the modulator, so there's the equation-based model. There's the slope compensator. There's the feedback amplifier, the voltage divider, output capacitors, and over here, that's all of my measurements. So that way I can compare the measurements to the simulations. Anybody here that's using ADS, these are free workspaces. You can download them if you want to run them, but it'll run on other simulators too. You just won't get the harmonic balance part. Now we look at the output spectrum. The output gives us all of the displays, the impedance, the PSR, the capacitor measurements, inductor current, switch time, ripple voltage, all that stuff. But again, okay, so how do you know I'm right? I played that funny game in reconstructing voltage waveforms so you could see ripple. How do I know that that's right? Well, I can compare the impedance and I know that's right because I did my measurement and my simulation and those agree really well. And there is my ripple waveform, and again, you can see that agrees really well with the exception of the little blips. These little blips are the switch times from the internal MOSFET gate driver, which isn't in my model. Certainly I could include that. I could even include the circuit board and it would be even a better reconstruction, but you got to admit, that's actually not a bad picture of the ripple. It's got good fidelity. When we put this into power distribution network, this noise is one of the largest noise sources. In the Xilinx case, one of the things I had to trade off were efficiency, switching ripple, and impedance. And so in order to improve their impedance, I had to give up something. What can I give up? I only have so many knobs. I can give up ripple, I can give up efficiency. In Xilinx's case, I actually had to give up both. But there's only so many things we can give up. I have an article in Signal Integrity Journal now that's called Power Integrity versus Power Electronics, the Ultimate Lose-Lose. And this also is a reason that we really want to have these high fidelity models. The power supply engineer looks at this ripple and says, wow, that's not really good. And I can see these spikes. I don't want the spikes. I'm going to put in some nice ceramic capacitors. And the ceramic capacitors will fix the spikes. And at the power supply, that's true. But what happens when you get to the high-speed circuit? What does that look like? Putting the ceramic capacitors at the power supply actually increased the noise at the high-speed chip. So let me get this straight. So you put the capacitors to get rid of the noise. If you take out the capacitors, you'd see that noise never made it across the plane. The high-speed circuit would not have seen the noise. So the power supply guy fixed the problem that didn't exist and caused one in the process. That's frequently what happens. That's why it is that we want all of these different knobs and why we need to know what controls what, because that's what allows us to balance all of this out. That's how we do it. How good is the Bode plot, the control loop? Do we get that right? Yeah, the model gets that right. Not a problem. We can optimize the PSR. I said there's a null point that's controlled by the slope compensation ramp. So we just adjusted the ramp a little bit, and we were able to give Texas Instrument 40 dB better PSR than they had. Is there a reason that they wouldn't want to give you that 40 dB? I gave a workshop at Texas Instrument this year, actually last year, and I asked them that very question. And what they said is they crank up the slope compensator because they're afraid that customers will get into problems with subharmonic oscillations. And I said, I just want to repeat this back to you because I want to make sure I understood what you just said. You said that you were afraid some of your customers might run into problems with slope compensation. And so you guaranteed them a problem instead. And I said, wow, that sounded stupid. I said, I didn't do it. You did it. I just said it. And they said, well, maybe we'll have to rethink that. But they took 40 dB of PSR away. Why would they do that? Doesn't make any sense. Can we simulate discontinuous conduction mode? Yes, we can. You can see the gain fall, so we don't have our flat impedance anymore. Our pedestal is rising. How do we know we're in discontinuous conduction mode? Because the model puts out the maximum and minimum voltages, right? The up and down points of the ramp. And so we can see when it gets to discontinuous current, the minimum will be 0. And so we can see right from that number 0 that it is in discontinuous conduction mode. I think I have a few more minutes. I just want to show you one more quick example of another board. This one I have here did the same thing, took all the datasheet parameters, plugged them into the model. There's the schematic, measured the inductor and the capacitor, measured the RI with a voltmeter, measured it with a VNA, measured PSR with an FRA, put in the parameters for the feedback amplifier. There's the finished model. Here's the little harmonic balance part that reconstructs the time domain for us. And we built 4 different versions of this model, including the one that TI built, or plus the one that TI built, just to show you that the model is capable of tracking them all. This one we put a really undersized gap so that we could see the excess inductance. That verified that the model got the excess inductance right. It also verified our equation. And then we did different impedances. We could set the flat impedance any place we want to by choosing different compensation values and different capacitors. And of course, we did TI's version also just to show how badly TI did using their own part. Ripple, again, we can do the simulation comparisons, and the ripple fidelity is really good. There's the impedance comparison. There's the PSR comparison. And one of the questions I get a lot is, what about multi-phase? And yes, it can do multi-phase also. This is probably not one of TI's better designs, but that's about as non-flat as you could get. And so I will take questions, but before we do that, I wanted to show something today it's actually kind of incredible. It's the first time it's ever been shown anywhere in the world. And that is that to make this measurement, this model, I said we made this model from measurements, and the measurements come from a number of places. We're measuring ripple for our correlations. We do that using a time domain oscilloscope. We had to measure PSR and control loop bandwidth, and we do those with a frequency response analyzer, a 3-port analyzer that measures voltage and current using 2 high impedance ports. And we also measured output impedance using a 2-port S-parameter analyzer. And for the very first time, we worked with Dgtronix, and we managed to get every one of those measurements into a single instrument, and we put it all into their Series 6 oscilloscope. So the Series 6 oscilloscope is capable of making every one of those measurements: the ripple voltage, the frequency response analysis, and the vector network analysis, and including the spectral plots. Everything is now in one instrument. It's the first time it's ever been done. It's not available yet, but it will be available probably by the end of this year. Where we're going to go next? Well, next we want the instrument to actually make the model for us, and we hope to get there soon. Next year we hope to get artificial intelligence into the oscilloscope so that it will tell us what it is that we need to tune from the measurements in order to meet our performance. And so if we can probably get that oscilloscope up on the screen just so I can show you what that looks like. The power supply itself has 5 different noise sources. Power supply rejection ratio, noise that comes in from the input that shows up on the output. The noise from the switching ripple. The noise from the transients. Yeah.
Are you talking about now a problem that I will have from EMI or?
No, I'm talking about voltage on your power rail. So how do you figure out what the target impedance is? The target impedance sets the voltage deviation that you're allowed to have on your power rail, your board, your PDN analysis. A big part of that is ripple. Another big part of that is power supply rejection-based noise, line transients. I do a lot of work with the automotive companies, and especially in Germany and in Detroit. And I say, here's a really good analogy. My wife wants to go shopping. I take her to the store and I shut the car off, but I got the accessory on. I'm listening to the radio while my wife shops. The car is on. I probably have 100 microcontrollers running in the car. There are FPGAs running in the car. I need to meet power integrity because all of those processors are running, right? So I am obligated to meet the voltage limits on all of those high-speed circuits while I'm sitting there. The car is not actually running, but the circuits are powered. My wife comes out of the store and she says, I'm ready to go, and I start the engine, and while the engine is starting, the battery bus is not 12 volts anymore. Now it's bouncing between 5 and 60 volts. Huge transients. Do I still need to meet power integrity? Of course I do. Now I got to meet power integrity with a 55 volt transient into the power supply. Of course some of that is going to leak out. How much? How much of the voltage that you're looking at in the power rail is going to come from switching ripple? Tomorrow, if you're in my paper, I'm going to show you something called jitter-induced jitter, a power integrity problem that comes from jitter of the switching frequency of the VRM. I worked on the GPS navigational clocks. There's 4 clocks in every GPS satellite, 3 rubidium clocks and a cesium clock, and they had trouble with the rubidium clocks. The problem that they had with the rubidium clock was the 1530-second harmonic of the switching power supply that got into the phase lock loop of the clock. And so would a resistor network show me that I had a 1530-second harmonic that was getting into a phase lock loop? Of course not. So I'm a proponent of end-to-end simulation. You got a power supply at one end, you get the high-speed circuits running on the other end, and we actually do simulate phase noise, including that's induced by the power supplies. We include everything. Good question, though. Anybody else have a question? Yeah.
How do we know to choose the right sample rate of the VRM?
The right switching frequency? So there's not really a finite answer, but I will give you some guidelines. One is that if you have a choice, you want to push the switching frequency to a band where you're not sensitive to noise, where you have your lower sensitivities. A lot of lower performance clocks have phase lock loops that are very sensitive in the band of maybe around 100 kilohertz. 100 kilohertz switching frequency would be a really bad choice for that. On the other hand, pushing the switching frequency up, well, there's some benefits. One is that you can make higher bandwidth, the filter caps get smaller, lots of benefits, but the losses go up. In some cases, we really have to make trade-offs. In the case of Xilinx, I had to push the switching frequency up to get the switching inductor to be smaller, to make the caps small enough we could tolerate. It wasn't an ideal choice, it was a trade-off. And so the higher you go in switching frequency, the smaller the devices are going to be, and the better the performance can be, with the exception of efficiency that's going to suffer. There are many switching regulators now up around 100 megahertz, 150 megahertz. We're hoping to get to a gigahertz in the next couple of years. I don't think anybody's accomplished a gigahertz switching, but we do hope to get there. How do we measure the PDN? We measure the PDN using our own 2-port probes on a vector network analyzer if we have the board. Very often we don't have the board, we just have the simulation files. If we just have the simulation files, then we connect our VRM to the board.
There is any importance of sample rate or rise time?
Sample rate for rise time. In power supplies, we generally don't really have rise time requirements other than initial turn-on. And the initial turn-on is very slow, so I'd say we don't really have a sample rate issue there. But the interesting point about your question is it's the reason that I wanted to make sure that we had a large signal simulator and not just a small signal simulator. That would be a good example where a large signal phenomena could come in. And that does occur. Yeah.
What about load regulation for proposed you method? I think you shift bandwidth to low frequency and make flat output impedance, but your impedance is bigger than a standard impedance.
Well, the impedance is set by the target line. And I'll tell you what I teach in our workshops is that there's a misconception about power integrity. In fact, my keynote in China was about that subject. Many people say that the goal of power integrity is to make the power rail impedance to be as low as possible. And I say that's nonsense. In fact, the exact opposite is true. Our goal in power integrity is to make the impedance as high as we can possibly tolerate. And there's a simple reason. If we want the impedance to be flat, it says that the Q must be equal or less than 1. That means the squared L over C divided by our target impedance must be less than 1. And if I rearrange that equation, you'll end up with something that says that C is equal to L over R squared. I talked about why we want to know this excess inductance, because that's L. C is equal to L over R squared. If I cut the resistance in half, it takes 4 times the amount of capacitance to absorb that inductance. Tomorrow, if you're in my paper, I'm going to talk about the fact that good regulation is a terrible thing. And in fact, I'm going to show you that the trick to fixing our clock problems is to degrade the regulation of our power supplies. Remember that what's really important to the chip is noise, right? Our load chips are sensitive to noise. And they may be sensitive to noise in certain frequency ranges. It may be sensitive to certain amplitudes. It may be sensitive to certain current perturbations. As a power integrity engineer, my job is to assess all of those and to guarantee that the chip got voltage that it liked. So what does it mean that the resistance is too high? The resistance has to be where it needs to be in order to accommodate the voltage ripple, the dynamic range, and all of the other things, the high-speed currents. And it's a relative thing. I have customers now that have single chip ASICs at above 1,000 amps, 30 microohm power rails. I have one customer who's going to hit 2,000 amps in a single ASIC next year, 12 microohm power rail. When you get there, it's challenging. It's challenging to measure and it's challenging to design for. The average chip like that has maybe 2,000 decoupling capacitors per chip. It's crazy. But 12 microohms is a really small number. So I would say that you got to be really careful. You know, the numbers are all relative. A low power circuit, you could have ohms of impedance, and at 2,000 amps, it might be 12 microohms of impedance. It just really matters what the total voltage noise limit is. And that's why I'm saying that you can't just use a resistor network, because the resistor network says, okay, we're going to take all of the other noise sources and we're going to just ignore them. And then we're going to do a calculation on something that's just based on dynamic currents, and then you're going to start to have problems because of all those other noise sources that you ignored. We need to consider this as one big ecosystem.
Well, maybe this is a follow-up to the previous question, but in your first slide, you rightly begin with saying that you consider all of the noise in the system, and then you showed an example in which, to alleviate some of the noise at the higher frequencies, you've flattened the curve by introducing what appears to be a load line at the lower frequency. Mm-hmm. And now your output voltage is depending on the load.
Of course.
And if we go to some of those extreme examples, like you said, we'd have a very large current swings at the target chip.
Yes.
You would have large output voltage swings.
Of course.
And the system essentially becomes nonlinear. How does that linear model takes into account the fact that your voltage changes in response to a current? And perhaps this is a broader question. To address that specific problem, a lot of the neurocontrollers are becoming nonlinear in their design.
Yes.
All those pulse skipping, digital control, all those gimmicks.
Yes.
How do we deal with that?
So a linearized model won't be able to deal with those. I'll answer your last question first. And it will tell you that all of those nonlinear control elements and digital control, I'm not a fan of any of it. I don't believe in any of it. I think that they're solving problems that they shouldn't be solving in ways that they shouldn't be solving them. And so it's kind of masking things. And most of it is really very simple. Now, you're right. As I raise the resistance, it's going to be more susceptible to current. Those current changes are going to induce voltage changes. And in very simple terms, the total noise of the chip is equal to the product of the dynamic current and resistance plus all of the other noise sources, right? And when I add all of those up, they all need to meet the chip requirement. I want to try to push that resistance up as high as I can because that's the damping of the network. If I have perfect regulation, and that means there's no damping. And if I have no damping, it means it's going to be extremely difficult for us to try to meet a non-resonant flat impedance. It just doesn't work. And so very often we want to push the impedance up. If you go back to that first slide I showed, and you guys do have access to the slides, so you go back to it, I showed our fixed version, which is flat, and I showed the TI version, which was not flat. The TI version has a peak impedance of about 125 milliohms. The flat version is 10 milliohms, 12 and a half times better. What TI is doing with these nonlinear controls and digital controls is to make up for the stupidity of that huge peak that they put in their impedance curve that they should have just designed out in the first place. It was easy to do. We designed it out with their part. We just used their part. We just reconfigured their design and we showed it as a 10 milliohm flat impedance. Why would I make this big peak and then try to push the impedance down by a factor of 10 to make it tolerable? That doesn't make any sense. It makes a lot more sense to put it where it is that we need it to be. Where do we need it to be? That's part of a budget. And that budget is made up of the voltage ripple, power supply rejection ratio transients, and dynamic current transients. And we can trade those off one for the other. Right? And that's what I had to do for Xilinx because they chose a power supply that had no controls other than the output filter and switching frequency. So I could control excess inductance by choosing the output filter inductor. And in order to tolerate lower filter inductors, I needed to push the switching frequency up. And I did this balancing, threading a needle, trying to get to where I could tolerate the switching losses and end up with a total noise budget that ended up meeting their chip requirement. And the budget was very different. I ended up with a lot more noise from ripple, but a lot less noise from dynamic currents. We don't care about them individually unless we're in an environment, for example, with like a clock, which I'll talk about tomorrow, which has sensitivities at specific frequencies. And then it's a little bit different. But in most high-speed chips, it's only about total noise budget. That's all we care about. Sure. Okay, I think we're out of time, but I just wanted to show you this picture because it's never been done before, it's never been seen before, and it was really exciting for Picotest to work on this. But that is two-port shunt through vector network analysis in an oscilloscope measuring a 1 milliohm resistor with a 400 picohenry excess inductance. And so now within the single instrument, we can measure spectral content, we can measure time domain, we can measure frequency response using a 3-port FRA, and we can measure vector network analysis using a 2-port S-parameter analyzer, all within a single instrument. Next, hopefully, we'll be able to export it all to Touchstone. I just want to thank you guys for giving me your time. I really enjoy talking. Like I said, you got to kick me to get me to stop sometimes. And again, I want to thank Dgtronix for inviting me, Dgtronix for supporting the instruments, and to all of you guys for showing up. So thanks.